This is the Husky Bites webinar series that we started in summer and are continuing this fall. This is the penultimate one of the season. There's one more coming up and I will show you those in a moment. Well, let me just, I'll show slides towards the end of this, but before we get too further along, I want to acknowledge the sponsors tonight, who are Jim and Nancy Nuremberg. Jim is a civil engineer class of 1980. So thank you so much for sponsoring Husky Bites. These sponsorships are not paying for Husky Bites. They are simply, it's money being used for student scholarships. And so if anyone would like to support student scholarships or their home department or anything at all, and would like to be acknowledged, please just let us know by sending an email to engineering@mtu.edu. So joining me this evening are two gentlemen. First, I'm going to introduce the co-host, which is Guy Meadows, and then Guy will introduce our featured speaker this evening. And so some of us may remember Guy gave one of the webinars this summer, actually, and I encourage you to look for that if you're interested in learning more about the images that we see right behind Guy's shoulders. But Professor Guy Meadows is a professor in mechanical engineering who joined Michigan Tech in the year 2012 after a long and distinguished career as professor of physical oceanography at the University of Michigan for 35 years. So he joined in 2012 to establish the new Great Lakes Research Center, which he led up until about 1 year ago. There's so much more I can say about you, Guy, but I'm going to leave it to the interested and curious person to kind of look back and watch your webinar, because almost everything Guy does is interesting, and he's a compelling and gifted professor. And so, Guy, I'm going to leave it to you to introduce Pengfei.
Great. Well, thank you, Dean Callahan. Pengfei, can you bring up the first slide? Great. Thank you. It's an absolute pleasure to introduce Professor Pengfei Shi. He's an associate professor in civil and environmental engineering and director of the Numerical Geophysical Fluid Dynamics Laboratory in the Great Lakes Research Center. Pengfei joined us from a background in mathematics and applied math at East China Normal University. He then went on for his PhD at the University of Massachusetts in Dartmouth. And there was one of the original creators of the new numerical modeling framework that is used universally across the coastal ocean and the Great Lakes. And we'll talk about that more in a little bit. He then went on and did a postdoc at Massachusetts Institute of Technology. And then we were able to entice him to come north to Michigan Tech in 2013. So a year after the Great Lakes Research Center was created, Pengfei joined us. Next slide, please. So as I indicated, Pengfei was one of the original developers of what is called the Finite Volume Community Ocean Model, or FVCOM. And the official definition of FVCOM is a prognostic, unstructured grid, finite volume, free surface, three-dimensional primitive equation coastal ocean circulation model developed by University of Massachusetts, Dartmouth, jointly with Woods Hole Oceanographic Institute. So what does that really mean? FVCOM depicts oceans using a three-dimensional grid that includes active thermodynamics. And what's important about FVCOM is that three-dimensional grid allows it to be an unstructured grid, which means each grid element does not have to be the same size. So that allows us to have tremendous information in places we care about, yet still solving the entire basin, if that's an ocean basin or a Great Lakes basin. So we can have tremendous insight in the surface of the ocean or the bottom of the ocean and the Great Lakes, or at the edges, which is what we call the coastline. So it's a very flexible model. Having active thermodynamics means it understands the coupling across boundaries like the surface. So it understands the thermodynamics that go on between the air and the sea surface. And when I say ocean or Great Lakes, I really mean both. The Great Lakes are really inland seas. Which means it's most applicably directed at climate studies, and the tools are the most advanced tools currently available for simulating the response of the global ocean system to forcing. And that is true with the Great Lakes also. So in short, FVCOM describes the three-dimensional motion of a compressible viscous fluid on a rotating Earth. So definitions are over with. That's what we're going to talk about, and you're going to see some very fantastic numerical capabilities, really state of the art. Next slide, please. We'd also like to thank both our sponsors and the number of graduate students and postdocs that work with Professor Shea on developing these tremendous numerical predictions. NOAA is a large sponsor of Pengfei's work. Funding comes through NOAA to the Michigan Department of Environment, Great Lakes, and Energy through their coastal management program. And you'll see some examples of the numerical simulations we are doing during this time of very high water here in the Great Lakes. We also work very closely with the Great Lakes Environmental Research Laboratory of NOAA located in Ann Arbor and have tremendous collaborations in developing these models in complex places like the combined Lake Michigan, Lake Huron model that accurately predicts the flows through the straits. We also work closely with the Corps of Engineers and greatly appreciate it of their support as well. Next slide. Without any hesitation, it is now time for Professor Shea to take over and tell us the fantastically exciting things that he's doing. Thank you all.
Thanks, Guy. As Guy mentioned, our research centers on the development and application of numerical modeling system. We apply the model system to address the climate and environmental problems in the Great Lakes region. The Great Lakes is the world's largest freshwater system. Approximately 34 million people live in this region. It supports 1.5 million jobs and billions in wages per year. This basin is also home to more than 3,000 species of plants and animals. The freshwater system is also an important shipping route, tourist attraction, and energy source. Often referred as the third coast, the Great Lakes hold a significant environmental, cultural, and economical values in this region, across the nation and internationally. The 5 Great Lakes, Superior, Huron, Michigan, Erie, Ontario, spans a total surface area nearly 95,000 square miles and are all connected by a variety of lakes and rivers. There are many fun facts about the Great Lakes. I list a few here. For example, Lake Superior is the largest freshwater lake in the world by surface area. Its deepest point is 1,330 feet. For comparison, the Empire State Building is 1,250 feet from the ground to the roof. So if you build the building on the deepest point of the Lake Superior, the building will sink beneath the surface on the lake. Lake Michigan shore is also the home to the largest fresh sand dunes in the world. For example, Sleeping Bear Dune, National Lake Shore, as well as many other protected dunes along the western coast of Lake Michigan, make up the world's largest collection of the freshwater sand dunes. Lake Michigan is also the only Great Lake that does not touch Canada. I'd like to ask you a fun question here. That is that collectively, the Great Lakes have enough water to submerge the entire continent of US in nearly how many feet of water?
Well, what's interesting is you have them as 10, 4, 1, or 7, which is interesting because they're, you know, the order of them is not just increasing in because I always just choose B by default. And B is winning. I'm just saying B is winning with 4 feet of water. So 59% of the people think that the answer to this is it would cover the entire continental US. Does that include Alaska? No, it doesn't. With 4 feet of water. Are we right?
How do we share this one? Should we stop sharing?
Sue has done that. So we were right. It is B. So we can see the answers, and it looks like B was correct.
I saw that it's about 10 feet, but maybe I got it wrong.
Oh, what is the, so I think
I think in my mind is 10 feet. I better go back to check.
All right, B was the most popular answer, so that's why.
B is the most popular one, but I'm thinking the answer is A. Math, you put the volume divided by the area of the United Continents, and you get the answer. So how do we do, oops. All right, so the Great Lakes are also the key elements. Oops, this one.
I know that previous question makes me worried now. What if the Great Lakes started to leak all over the US? Now we'd all be underwater.
The Great Lakes are also the key elements of the regional climate. They are not only influenced by the regional climate, but also a significant regional climate driver. Due to their large volume, heat capacity, and geographic extent, and the thermal inertia, this Great Lakes plays an important role in influencing the local weather patterns and also climate process. With the global warming, some of the key climate processes are changing, accompanied by the change in the Great Lakes. These changes further impact the lake ecosystem, such as fish habits, water quality, and regional hydrology and water resources. They all have a significant public and economic impact. So for example, we have seen the warming trend on both global and regional scales. On the top left panel, the graph illustrates the changing of the global surface temperature relative to 1950 to 1980 average temperature. Actually, 19 out of 20 warmest years all have occurred since 2001, with one exception of 1998. The lower panel is actually showing the 5-year average of the global temperature. The dark blue is indicating the cooler than average. The dark red indicating the warmer than average. If we look at their evolution, then if you take a look at that, what you see is from 1960s, we can see a very clear pattern of warming from 1960 to until now. You see it's become all red.
Wow. Goodness.
Yeah. Then for Great Lakes region, we see the similar pattern. For example, this figure shows a summary since 1951. We see the annual increase. The annual average air temperature have increased by 1.3 degrees C. And the total annual precipitation has increased by 14%. And the frequency and the intensity of the severe storm has also increased. This regional climate has a profound impact on the Great Lakes system. For example, the reduced ice coverage in the lake allows the more evaporation to the atmosphere, interacting with the cold air coming from the north in the cold season, causing a severe lake effect snowstorms. Rainstorms in combination with rolling waves and rising lake water level can cause severe coastal flooding, erosion. Hydrological intensification also influence the nutrient removal and transport, along with the intensified lake thermal structure or stratification. It can increase the harmful algal blooms. The climate change is not only about the trends, One of the important concepts in the climate change is to understanding the variability across a wide range of spatial and temporal scales. The figure here is showing that more than 90% of the ice cover on Lake Superior on the February 19th, 2014. It is amazing to see, you see the wind push the massive ice sheets to the northeast, opening the South Shore. So the fun question number 2, let's see who is right. Can you guess what was the ice percentage on February 18th, 2070, pretty much exactly in 3 years? What is the answer? What is your guess?
So there's 4 different choices. The first choice is 67%. The second choice is a little bit bigger, 96%. The third choice is 25%. And the fourth choice is 8%.
Right.
And so the most popular answer is 67%. And of course, I don't have even the wildest guess, but I actually think if I were to guess, I would say C, 25%. All right, so.
Okay, the answer, if you look at here, it's actually 8%. It's ice-free.
That's astonishing. That's a huge difference.
Right. That's but we have to be careful because notice that this dramatic change in the ice coverage between these 2 cases does not directly reflect the trend of ice reduction. Okay. The figure on the bottom right shows the long-term annual maximum ice coverage since 1973. While we do see the trend of the ice reduction over more than 4 decades, it is also important to know there was a large interannual variabilities. So what we're seeing is the interannual variability rather than the direct linear trend. This large spatial temporal variability is seen in many environmental variables, water temperature, circulation, wave, and many more. The complexity in many of these processes, as we just seen, are regulated by the interactions among the atmosphere, lake, ice, and the surrounding land areas that heavily influence and regulates regional climate. The lack of a fully integrated regional model has not only added additional uncertainty to the future climate projection, but also limited our understanding of how the atmosphere, land, lake process interact with each other in the context of the Earth system change. So we focus on developing an integrated regional Earth system model, or IRESM, for the Great Lakes region, consisting of the coupled atmosphere, lake, ice, wave, sediment, land surface, biological components, with the inclusion of the data simulation and machine learning techniques. By applying the IRESM to simulate the regional process across the spatial temporal scales, we try to understand or predict how the Great Lakes system responds to the long-term, short-term, natural, anthropogenic disturbances as the climate variability, extreme events, coastal hazards, or lake biophysical processes. The observed global warming is projected to continue into the future and likely at a fast pace. The warming rate also depends on the climate scenarios. RCP 8.5 and RCP 4.5, which broadly represents the high and medium rate of the increase in greenhouse gas concentration. For the Great Lakes region, the average air temperature are projected to increase by up to 3.5 by the mid-century and increase up to 7.2 degrees C by the end of the century under different emission scenarios. This change may exacerbate the existing vulnerabilities and creating the new risks. So here we present a few examples of the cascade impacts of the large scale climate change on the regional scale using the water level change as example, and on the local coastal hazard using the medial tsunami as example. Let's first consider the impact of water level change. There has been a large swing of the water level from the nearly 15-year extremely low to the recent extremely high in the past decade. The water level has been trending upward at a varying rate since 2013-14, when the Lake Huron and the Michigan fell to their lowest points, and the other Great Lakes were significantly below their normal level. The Great Lakes level are known to fluctuate over time, but the study have shown that the prolonged low water level and the more recent rapid rates are likely associated with the warming climate. So our third fun question is, which is the following has a significant impact on the water content and lake level of the Great Lakes?
All right, and so there's 5 choices. Precipitation falling over the lake, evaporation of water from the lake. So can you answer more than one?
Should be just one.
Which is the most significant? Okay. Surface runoff from the lake's basin into the lake. A and C, or A, B, and C? Ha. Mm-hmm. Wow. A, B, and C. That's my guess. Nearly everyone is going for A, B, and C. At 77%.
Right, that's the correct answer.
Good, good.
As we have seen in this question, the primary driver of the water level in the Great Lakes are the overlake precipitation, evaporation, and runoff into each lake collectively. They are called the late basin supply, or MBS. And of course, the interlake flows are also important factor to the water level of each lake, but they are the response or result of lake water level change rather than a driver. The projection of lake water level has great uncertainty and very challenging. Here we present a model framework that we have built for projecting the water level. First, let me go through this with you. First, the output from a set of the global model projection is used to drive our regional climate model, or RCM. The RCM is helping enhance the regional details through the more realistic representation of the regional physics and dynamics. Then the RCM provides the projected air temperature and overland precipitation to a large basin runoff model, or LBRM, to project the basin runoff. And meanwhile, the RCM also provides the overlake precipitation and evaporation. Therefore, we now obtain the changes of net basin supply. Remember, we just talked about the definition of net basin supply. By inputting the future net basin supply into the coordinated Great Lakes regulation and routing model, or CGLRRM, which resolve the interlake flows, we complete the water budgets of each lake and project future water level change. So this figure here presents some of the scenarios of future water level change in Lake Michigan by the mid-century. Most of them projected a continued increase in water level at various magnitudes. One of the projected future water level could be 0.8 meters higher than our baseline period, which is the average between 2000 to 2019. Remember, in the above, we just talked about the climate projection and the regional impact on the water level. Now let's look at their cascade impact on the local scale, the coastal hazard. On April 13, 2018, a high amplitude atmospheric inertial gravity wave packet crossed the Lake Michigan at a propagation speed that neared the long wave gravity wave speed of the lake, which produced a protoman resonance. This induced a set of medial tsunami waves that struck the shoreline near the Ludington. That is a coastal community along the sandy dunes of Lake Michigan. During this event, as you see from the video, the harbor walls were overtopped. Damage occurred to the shoreline homes and boat docks. This video shows the flooding in the region marked in the red circle here.
So wait, what is a gravity wave?
Oh, the surface gravity wave is a wave induced by surface gravity. Therefore, they call surface gravity wave. And that occurs both in the atmosphere as well as in the ocean. So
I've never heard of it.
Surface gravity is a driving force of the wave. If you throw a stone in the water, you see the wave propagates.
Mm-hmm.
That's one of the wave caused by surface gravity.
Okay. Huh. Interesting.
But if you're considering the Earth's rotation, there's an inertia too. So it's more complicated than that case. But I think that's a short answer to you about surface gravity wave.
Thanks, yeah.
So in our current study, we worked with a Nova Galera scientists, including Dr. Eric Anderson and Philip Chu, to build the next generation high resolution coastal forecast system. We're incorporating the advanced model functions to simulating the wetting and drying over the nearshore land area, and also resolving the water overtopping over the breakwater. And we revisit this event using the newly built model. What you see here is that when all this detailed hydrodynamic process and the geometry were properly resolved using our model, the model produced a very reasonable simulation of the flooding area. Furthermore, we assess what the impact of the medial tsunami would be if the water level is higher. We presented two scenarios. The first one is called, we call it the likely scenario. We run the model in combination with a recent high water level, for example, in 2019, which is about 0.8 meters higher than the real water level during this event. We can see the flooding becomes much more severe and a larger region will be impacted if the same storm occurred in the higher water level case. The second scenario we call it perfect storm, which we increased the storm intensity by 50%. And in combination with the high water level, the model projected by the middle of the century. That is adding additional 0.7 meters higher than the water level in the likely scenario. So what do you see? The flooding become way more severe. Here, just make it a little bit more easier to understand or to see the results. We create a 2D animation of the likely scenario and the perfect storm. And we can see how the medial tsunami wave struck to this area. Let's see if I get this 2-1. So I'll just play each one more time. That is how you see this wave cause the storm surge and the coastal flooding. We also did a 3D simulation that is for the perfect storm case and showing the water level change and the arrows represent the currents, how this region would be flooded in a intensified storm with a really high water level in the future.
Well, and these look like highly residential areas.
Right.
Yeah.
But again, this is just a scenario. When in order to predict water, all the projection of water level change has a great uncertainty. And we have identified all the studies have identified the relevant uncertainty and the spread of the future projection. And this is the case we see. You could consider that's the worst case scenario by combining the really high water level with a big storm.
Yeah.
Um,
And is it concentrated in these areas because of those underwater barriers? Is that why it seems to be focused on those areas?
Yeah, that's a protection. I think if you're talking about outside the breakwater.
Mm-hmm. It almost seems like it focuses the energy into that area.
Right.
Well, I guess it does. Yeah. Wow, this is fascinating.
You could also see this eddies shedding because when the water passing this the mouth of the breakwater and this narrowed lake between the inner harbor and the outside. It's caused the eddy structure there.
Oh, right. Yeah, I can see that. What is the time scale of this? Is this sort of like a 5-minute thing or
the entire simulation is a couple hours.
a couple of hours? Okay.
Yeah, and that's also the challenging because things come here really quick. Okay, so our fun question number 4, that is related to another example of how the modeling to use the modeling to assess the environmental impact. I don't know how many of you have remember or heard the independent risk analysis for the Strait of Mackinac pipeline in 2018. This pipeline conveys the petroleum via the Great Lakes states. The Line 5 is particularly notable for passing the under environmentally sensitive Strait of Mackinac. And many of you are have remembered that. That's great.
Yeah, well, 60% of us remember this.
Yes, and Dr. Meadows will tell us the story about it.
Thank you, Pengfei. Appreciate it. So could you back up one slide? Let's stick on that slide for just a minute.
Oops.
So since 60% of you remembered that, I need to tell a little bit of story here that's history, perhaps for the rest of you. So the previous Michigan governor, Governor Snyder, created a pipeline safety advisory board to provide input on the future of Line 5 across the Straits of Mackinac. And I was honored to represent Michigan's public universities on that board. One of the things that we did as a board is we created a scope of work for 2 massive studies of the Straits of Mackinac and the petroleum pipelines. The first study was the alternative analysis. If you wanted to move the same amount of oil that the pipelines presently move, what other ways would you consider doing it? Railroad, barges, those types of things. And the second scope of work was for a massive study called the independent risk analysis, which was to define what are the risks associated with the worst case spill from the pipelines and what were the total costs of everything to do with that spill. Both of those scope of works were published in several consulting firms responded to those. The independent alternatives analysis went to completion, but the independent risk analysis was terminated 2 days before their draft report was due to an undisclosed conflict of interest with Enbridge, the owner of the pipelines. So the Pipeline Safety Advisory Board asked me, who I representing all of Michigan's public universities, to put together a university team to take on the risk analysis, which by this time was a year late behind the alternatives analysis. So if I could have the next slide, please. So we agreed to do that. We felt that Michigan's university had an obligation to the states to do that. We formed a team of 9 universities, 7 of which were Michigan universities and 2 outside universities, to undertake this enormous analysis, which involved 42 researchers. And keep in mind, some of us knew each other, but mostly this is our first time working together. And our task was to first define what is the worst case scenario that is plausible and feasible to happen. Then once you have that quantity of oil, where does it go? How does it get there? Where does it end up? And then what are the total costs associated with cleaning that up, the cost to public health, the cost to native communities in terms of change of way of life, cost to the ecology, what is the ecological cost, what are the costs of restoration, what are the natural resource damage costs, government costs, and finally public and private costs, and to add that all up, which, as you can guess, was a fairly major undertaking. Next slide, please. And they gave us a 6-month timeline because it was already late because of the failure of the other consulting firm. So Pengfei was the chief scientist for the second part of that operation, that is the fate and transport. So how do you determine where a massive spill like this is going to end up, given the complex flows through the Straits of Mackinac, where Lake Michigan and Lake Huron are constantly interacting with each other? So a very major undertaking. We decided to use the actual weather that occurred in 2016. So from January 1st of 2016 through December 31st of 2016. And this was done in very close collaboration with the Great Lakes Environmental Research Laboratory of NOAA in Ann Arbor. And as a result of this effort, we have greatly advanced the state of numerical modeling in the Great Lakes. And a little aside there, we're better than the ocean coasts because about 30% of the US and Canadian populations drink the water from the Great Lakes. So it's very important that we know how the water moves here. And that has resulted in a tremendous 20 to 30 year effort to be very good at predicting model flows. And Professor Shea's work here has with partnerships at the NOAA lab have advanced that tremendously. So they did a series of 4,380 simulations. And how did you get to that number? We did a simulation for every day of 2016 with the actual weather that was occurring over the northern Great Lakes at that time, every 6 hours, so 4 times a day for 365 days at 3 locations across the straits: north side of the straits, center of the straits, and south side of the straits. And for each of those, if you multiply that out, that's 4,380 simulations. And each one of those simulations, the team released 10,000 particles that simulated how oil would behave and tracked those particles every place they went for at least 60 days or until they went to onshore. So an enormous effort. And when the Great Lakes Research Center was created in 2012, the university made a tremendous commitment to the Great Lakes and added a supercomputing cluster in the Great Lakes Research Center. And that cluster was used extensively for these simulations. So I'd like to show you the worst case scenario in the next slide. This will take a little bit of explanation here. So this is a slide that happened in the real weather in 2016, 2 days after Christmas, December 27th. So it's that weather that is driving this. You're seeing in red the percentage of particles that are still afloat, and in green, the percentage of particles that have reached the beach and are grounded. So notice how quickly we're now 100 hours into that simulation, and the oil has spread over a large distance of northern Lake Huron and is now impacting the Canadian shoreline. And by this point in time, 98% of the oil has been beached and only 2% of the oil is still moving in the water surface. And it is finally beaching here at roughly 300 hours into the simulation. So next slide for a summary. And again, this was done 4,380 times. Have we lost the slide?
Why don't you stop share and reshare, Dr. Shea?
Okay. Something.
Great, thank you. So the movement of the oil is dependent on the weather in the hours and days after the spill. Depending on that weather, oil moves into either one lake or both lakes. For those flows that flowed into Lake Michigan, the maximum shoreline that was impacted was 1,021 kilometers. And for the worst case flow that we just saw into Lake Huron, almost twice that number, 2,006 kilometers of shoreline were impacted. So again, for all those simulations, these statistics and the fate and transport of the material is known, and the team advanced the state of our ability to predict these flows tremendously by their work. So Dr. Shea has done a tremendous service to the state and to the universities. So we'll glad to answer questions now. Next slide, please. Thank you all very much.
Thank you.
Very good. I'm gonna take over for a moment and share my screen. And I'm going to present just a couple slides. And then while I'm doing that, I want to encourage our audience, which is very substantial, to use the Q&A to enter questions in the Q&A. And then following me speaking for just a moment, we're going to answer your questions. And so first off, Dr. Shea, Pengfei, and Dr. Meadows, Guy, thank you so much to both of you for spending your evening with us. I learned a lot. I have two new vocabulary words, surface gravity wave and tsunami, that I'm going to actually look up in more detail after the show. So thank you so much. It's always great to learn something new. I want to thank again our sponsors this evening. Really appreciate the sponsorship of the Nurembergs. We're not doing that poll right now. I do want to point out that our last webinar of the season occurs 1 week from today on December 7th. And this is going to be focused on the phenomenon of that you learn about when you live here, which, by the way, nobody warned me when I was coming into Keweenaw that it would snow every day. But, you know, I've learned to like it because it makes for high quality skiing, for cross country skiing. But there's a phenomenon that's associated with Lake Superior being all around us that results in lake effect snow. And so we're going to learn about that with Dr. Ray Shaw from the Department of Physics, with co-host Will Cantrell, who is also in the Department of Physics and who is now the Dean of the Michigan Tech Graduate School. I do want to point out we're then going to take a break for the holidays, and we're going to start January 25th, Monday, January 25th, and we will have a lineup posted on the Husky Bites website. I mentioned these the last few webinars. I do want you to know there's a whole enormous series of certificates that are being approved and have been approved that I want to draw your attention to. So what is a graduate certificate? It's a cluster of 3 classes that together form a credential. It's about 1/3 of the effort that's required to earn a master's degree. These certificates are stackable, so you could earn a certificate and then later on decide you want to take another 1 or 2 and thereby earn a master's degree. They are entirely available online. And so that's the first group of them, all in the Department of Civil and Environmental Engineering. This is the second group that were approved. And you can see their titles corresponded to all kinds of different areas. We have approximately another 10 in the process of approval. And so if you're interested in learning more about these, just please send an email to engineering@mtu.edu. And if you are interested in giving to Michigan Tech in support of anything at all, and you would like to be acknowledged on Husky Bites, we will associate your name if you wish, or you can be anonymous with sponsoring a webinar, which is awesome fun for me. Thank you. So I'm going to stop sharing my screen and return to our speakers. So now you should see, yes, you can see Guy and Pengfei. So we've got 23 open questions. Holy cow. So we'll take turns with these, Guy. I'm gonna take the kind of first one. So we were chatting about, we were chatting about the fact that I went out to the camp this weekend to spend some time, and this is where my husband had distributed these enormous boulders in order to protect the coastline, which is related to what we're talking about with the rising lake levels. And so it's out, that camp is out in the direction of Lance in Ora, which is on the direction along the way toward Point Abbey. So that's the answer to that question, Amy. So Pengfei, I have a quick question for you. So is Lake Superior going to rise anymore, or is my camp safe?
So that's a good question. From long-term, based on our current simulation, I think there is a chance, or the projection is leaning toward to a continual rise. We don't know for sure about the degree and the magnitude of increase, but based on our current study, we believe so.
Well, that means that the money my husband just invested in all those big boulders was probably well worth it, I think. All right, Guy, do you want to take a question? You could take them in any order.
I just might add a little to that last one too, that what we're seeing in recent years is increased variability. So we're seeing very high water level episodes that last several years, followed by very low record-setting water levels. So I think the future, independent of what happens with the mean water level, I think we're going to continue to see extremes. And Pengfei led off with a good example in looking at ice cover, how much in a year or two conditions can change in a body of water the magnitude of Lake Superior. Will Cantrell had a question: how much of lake effect snow that I shovel off my roof runs off back into the lake in the spring versus how much is exported downstream or other parts of the Midwest as vapor in the atmosphere? Pengfei, do you have a guess on that one?
I don't have a guess on that one, but I think that's that's a good question regarding the water budget on the portion of the in the large hydrology and the water cycle, how much it goes to different routes, and what is the change in the route into the future when we have a warming climate, temperature, would those evaporation would change, or slow melting would also change not only their total magnitude, but also their seasonality. And I just don't have the answer to that good question.
Yeah, well, certainly a lot more snow evaporates than melts is my observation. And I have no idea what the ratio is, but so there's a lot of questions about surface gravity waves. And so John Soering has posted a Wikipedia link so we can all look it up later, the gravity wave of what a gravity wave is. But there's 3 questions from Eric Peterson that I think I want to take next. So he has seen lake levels change over a short period of time due to significant strong atmospheric pressure changes over a short period of time. Is that different from surface gravity, or is that so lake levels change over a short period of time due to significant strong atmospheric pressure changes over a short period of time? How can that happen, actually?
That's the atmosphere disturbance, the pressure change. When we talk about the tsunami, of course, the tsunami happens in the ocean. That is because, an earthquake causes sound movements in the ocean bed. That creates the sound move of disturbance to the water. In the medial tsunami, the cause is because atmosphere that could be a squall or a thunderstorm, anything that produce the disturbance. It's similar to you throw a stone in the water, but different scale. That disturbance caused the water level change initially, and because of the restoring force of the gravity.
I see. So it's the atmospheric change and the weather that triggers it, and then
exactly
what propagates it is this, and then it propagates basically.
Yeah.
Okay, that makes a lot of sense. All right, and then the follow-on question to that is how have you validated the models?
I don't see the question here, but which models, or if I could?
Well, maybe you could describe one of them. So is there any way to validate the models?
So that's a necessary step, and because we know that observation give us ground truth, the limitation of that one is scattered. You cannot get everything at any point for all points for all time. On the contrast, the model has the ability to produce continuous 3D in space evolution of the state, whatever that means. Maybe the water circulation, maybe the temperature, everything. So the trade-off is that we don't know what the model gave us is how good it is. We need to validate the model, and often what we do is to the scale assessment. We use the observation compared with the model produced results. Mm-hmm. Then intuitively, if we see the model produced results have a good agreement with the scattered observational data, then that gave us the confidence of the in the model performance. So we trust the model more. And if the results not in a good agreement, that warn us we should further improve the model. There's many things we could do, but let's all go to the model development. So all this model here we presented, the results has been validated across the different array of the observational data. Just because for the time being, we didn't present that. But in terms of the observed phenomenon, as well as the modeled temperature currents, that's why when we talk about model, it's really an integration of model and observational data. Model itself couldn't do anything. Only modeler believes their work without validation. So yes, we did the model validation by comparing this model performance with observational data.
And recall, we have a network of about 30 surface buoys across the Great Lakes, as well as subsurface instruments that the universities of the Great Lakes deploy, as well as the NOAA lab in Ann Arbor. So there's a tremendous amount of that observational data that is used, and particularly in the example of the Straits of Mackinac, the comparison between the model and the buoy measured currents were tremendously close. The modeling has come a very long ways.
Very good. Guy, do you want to?
Yeah, I'd like to answer a question specifically to me.
Okay.
He said he read that your dad used to, well, I talk about that. My dad used to give me the fun math problems to challenge me when I was a kid. Then actually made me very interesting about the math and physics, which is closely related to what I've been doing. And the question is, do you do that with your own kid now? What is the best way to get kids to enjoy math? That's a good and a tough question. Yes, I do. I tried the same way. I don't know how it is working, but what I think the most important is, no matter what I do with my kids, by playing games or pose questions for fun, is strengthen the tie, a connection between us. And I try to find the opportunities to show them the math is important in our daily life. I think one thing I learned, because I majored in mathematics, is that I learned a lot of math at the beginning, but sometimes I was get lost. Why do I need so many maths? What is the knowledge? And why do I need to learn it? Until I found, oh, there's a great applications of all kinds of math. Use maths and physics to solve those questions. That really inspired me. So I'm trying to do the same to my kid. I think it's stating as a site, as a guide, I think it's the strategy I would like to go, or what I'm trying to do. When I observe, when they have the interest to something, I'm trying to say if I can inject something there related to whatever I want to teach them. Maybe math, maybe other things, but that's a strategy I'm practicing. So.
Oh, I think you're probably a really good dad, and clearly you're an outstanding educator. Yeah, no, it's always challenging. Guy, do you see a question you'd like to handle next?
Yeah, there's one from James Nuremberg. Assume that information has been shared with the city of Ludington. And part of the reason that we have the funding from Eagle to look at these high water scenarios and what might be in the future for the Great Lakes is because we also, through that same program, have a group of people where we work with communities like Ludington along the shoreline to help them become more coastally resilient. What sort of things can they, once you see Pengfei's simulations, you see what part of the city is vulnerable and what do you do in your zoning laws to change that and become more resilient. So it's a very important part of taking that next step and trying to get these communities to think about how bad things could be or how good things could be in the future. and how to plan accordingly in the face of a lot of unknown and a lot of uncertainty.
So Margaret has a question. The simulation makes it look like Canada should have a higher stake in keeping the pipeline healthy. Who is responsible for the pipeline's health?
Everybody is responsible. The pipeline company, Enbridge, is responsible. The U.S. government has a say through the Department of Transportation. The Coast Guard has a say, and we were surprised to see some of the number of these simulations that did move oil particles into Canadian waters. That was somewhat of an unexpected occurrence for us to see that, and how quickly it did. So certainly the Canadian government is aware of these conditions as well. And there was another question that had to do with pipeline, and was the quantity of oil in the worst case scenario, which was 58,000 barrels, and there's 44 gallons in a barrel, as the petroleum industry goes. So that's the total quantity, 44 times 58,000.
Pengfei, do you see a question you'd like to answer?
Yeah, there's a question, was the Ludington from Nielsen, was the Ludington event simulated by wind? I think he is asking how we drive in this hydrodynamic model. By working with NOVA, what it is there's a couple steps to do the simulation. The first, I think Greg Mann at NOVA built a WOLF model, weather forecast model. Using that model, where this model simulates the atmospheric conditions. Most important is atmosphere pressure and the wind. And these two, and along with other meteorological variables, being used as a driving forcing of the hydrodynamic model. Then that is the atmosphere pressure gradients as well as the wind to drive the circulation, the currents in the lake, as well as the water level change, cause the flooding and the wetting and drying, what we see in there. So, but in terms about the dominant force, I think in this case, the atmosphere pressure disturbances is much more important than the wind. So by inputting the wind along into the model, we wouldn't see the large meteor tsunami.
Oh, that's interesting. There's a comment from Carrie, class of 72, Carrie Irons. We live on the east end of Lake Makatawa. We are in Holland, Michigan, 5 miles inland from Lake Michigan, but connected to the lake via a channel, and so we're at the level of Lake Michigan. On a day with a strong west wind, we can see a 12-inch rise in lake level in less than an hour. It's kind of astonishing.
Right. Wind also has a very important impact to the lake water level change. They could produce a meteor tsunami wave. They also could produce the siege wave. That is the water when there has a strong water push when there is strong wind push the water against the shoreline. So that's a setup. When the wind is released, there's a large fluctuation across the basin. So wind is definitely important, but often when we talk about storm or thunderstorm or front, there is a combination of the atmosphere pressure gradients disturbance as well as the winds. In different situations, they all play an important role. But in this particular case, we actually use a model. One of the good things to use model is we can turn on or turn off, particularly driving forcing. And then we can quantify the contribution of each of these mechanisms to this event. That's why how we know in this case, the atmosphere pressure is more important than wind speed itself, although the wind is also much.
No, you must be, I'm really, so following the webinars at exactly on the hour, which is right now at 7 p.m., I'd like to thank our audience for joining us. And then I also want to say that we're going to stick around and answer some more questions. And we still have 25 open questions. So in terms of thanking, not only do I want to thank the audience and our sponsor this evening, but I want to just thank you again, Dr. Shea and Dr. Meadows, for your time. Dr. Shea, I'm just blown away by the complexity of this model and how many factors need to be taken into account in order to do a tremendous job. You know, these kinds of estimations are so critical because people need to decide where to invest in order to protect and all kinds of critical things. So thank you for giving us your evening, and thank you, audience, for joining us. And we're going to go ahead and take some more questions. Guy or Pengfei, do you see a question you'd like to answer?
There's another pipeline question about what was the total cost of the worst case scenario, and that number was $2 billion, just under $2 billion. And the end result was that Enbridge now carries an insurance policy for that much as an insurance policy against a worst case spill. That was a requirement of them continuing to operate the pipeline.
That is interesting. Yeah, no, yeah, I'm not going to comment. I'm just going to. Well, then a related question about money is from Michael concerning Great Lakes water levels. So the highest model increase of Great Lakes water levels, in addition to added flooding, do either of you have any idea what that would result in? What kinds of damages and costs?
After the high water level in 1986, we started a program with the state to actually survey 45 permanent sites along the Lake Michigan and Lake Huron shoreline. And we surveyed those annually from the top of the dune to a depth of about 10 meters water depth, 30 some feet offshore. So the whole profile to understand how the lakes and the shorelines recover from a severe water event like we're going through now. Unfortunately, we weren't probably any more prepared, in fact, least prepared for this than we were in 1986. But what we found through those whole efforts is that water is the enabler and the storm waves are what really cause the damage. So as storms bring, and this gets back to a previous question, as storms bring precipitation that falls both on the land and runs into the lake, but also directly on the lake surfaces, our water levels begin to come up. And as those storms become more and more frequent and more intense, water levels increase with that increase in storminess. And we've seen that through the last cycle from high water to low water and now back again. But the wind that comes with those storms also makes waves. So the wave energy actually increases as the storminess increases, as you might expect. So during high water years like we have now, wave energy at the shoreline is actually 25% greater than it was during the low water years. So those big boulders that you just invested in are seeing bigger and bigger waves while water levels are high than will be incident at the shoreline when water levels are low. So the shoreline damage, which was the original question, occurs during the peak in wave energy, which is about 18 months before the peak in water level. So as water levels coming up, it changes where the waves are able to work on the shoreline, and the most dangerous place for the shoreline is when waves can strike right at the base of the bluff, which is what causes very rapid coastal erosion. But it's the wave energy increase that's happening before the peak in water. So that's why I'm optimistic. Water level is turning down. Last year started down in Lake Superior. This year it's starting down in Lake Michigan and Lake Huron, which means the storminess is decreasing as the storm tracks change and less storms come over the basin.
That was very helpful. Well, so yeah, no, I have so many more questions, but we have 25 open questions still. So this next question is from John, and I think it's for Pengfei. As the climate warms in the Lake Superior water basin, should we expect to receive more lake effect winter precipitation as ice coverage on average reduces?
So that's a question I was going to answer. There's a similar question is, unrelated question is talking about the winter. So I think I could combine them. Another question is about in the winter of 2017, Lake Superior only have 8% of ice. That winter also has not just snowfall from the lake effect. So I think that's a good way to look at this, talking about how the lake effect snow forms. The formation of lake effect snow is really needs the moisture supply from the lake. So in fact, if the lake is fully covered by ice, like a cap, there is no moisture supplied to the cold air when it's traveling above the lake. We won't get the lake effect snow. So when we have the cold air from the north, in combination with the open lake that provide the moisture, that air mass, like a sponge, getting a lot of the water vapor. Then when it's travel over land, that produce a precipitation in the form of a snow. So in a warm winter, it does not mean it wouldn't get lake effect snow. As long as we have the short-term cold air mass traveling over the lake, it could happen, and it could happen in a severe magnitude. And that actually leads another question: what's happening in the future? Because in the future, with a warming period, one thing we could think intuitively is that because of warming, so there is more precipitation occurred during the winter in the form of the rain rather than snow. So that's one thing you could think about because temperature warmer. But on the other side, the warming on the global scale, particularly for the Arctic Ocean, that could destabilize the jet stream, which is constraining the cold air mass near the Arctic Ocean. So the meandering would allow the cold air mass more easily from the higher latitude to intrude to the North America and Great Lakes region. So that provide the cold air mass. Number two, because of the warming, during the winter time, the lake is free, open, without the ice coverage or less with ice coverage, and that's moisture there. When you have the cold air mass, you have the open lake, we can get severe, even more severe snowstorms. But how long this trend would occur into the future, or if this climate would essentially because so warm, so the majority of the form of precipitation becomes the rainfall. I think they're both happening at the same time. We have the more severe the single storm, but we also have in general total amounts, we have more winter precipitation in the form of rain. Then this is a good question. We see, or this is an interesting study. We could use a model to predict these competing factors between the large scale forcing, the local interaction about the ice and the air, to look at the results.
And in this fall season, when the lakes are warm and the outbreaks of cold Canadian polar air, as Pengfei was talking about, makes the boundary layer in the atmosphere turbulent and allows for more momentum transfer from the wind into the water surface, which makes our waves bigger. And if you look at the history of shipwrecks in the Great Lakes, they all happen this time of year, November and December, because for a given wind speed with that increased momentum transfer, waves can be twice as big as they are previously forecast to be. And that's what happened during the Edmund Fitzgerald event, is that the warm water and the cold air over produces an air sea temperature difference that is almost unheard of in the ocean environment. it's unique to the Great Lakes and results in very dangerous wave conditions this time of year. Plus a lot more snow.
Yeah. All right. So now we've got a question from an anonymous attendee. Do either of you think there's a chance of one of these medio tsunamis type waves to hit on any of the other Great Lakes, including Lake Superior? And thank you for your great talk.
Yeah, that's totally, I believe it all. I haven't looked at the historical situation because we used this as a single case to revisit the model and looking at the coastal flooding. But if we think about the mechanisms why this meteor tsunami occurred, that's really because when there is the produced surface gravity wave, the wave propagates when the weather system also propagates at a similar speed. And by the way, the wave propagation in the lake is related to the water depths. So when these two are traveling at a similar speed, that causes resonance. The wave get larger and larger and larger. Then it causes the coast flooding. So that could happen to that's why we say when it in the right condition, when the direction and the weather system move along with the traveling speed of the wave in the Great Lakes, that could occur. I think it occurred in the Lake Erie, maybe Lake Superior, but I have to admit, I don't look at the historical data, so that's my guess. But from the mechanisms point of view, it's absolutely possible. Just a chance of large or small.
So we are running out of time. You know, I feel terrible because there's still, you know, a whole bunch of open questions. Guy, if you want to pick one last question to answer, and then Pengfei, if you could take the last question, I think we're going to need to conclude it there because I've been trying really hard to end these at 7:15. So I apologize to all the people whose questions we haven't been able to answer. But
For the ones we don't get to, please feel free to send us emails and we'll be glad to answer them that way.
Oh, that's a good idea. Maybe could you guys in the Q&A or in the chat just put your email address in? That's a great idea.
Sure. And there was one about the flows. You wanted me to answer one more? One question about the flows in the Straits of Mackinac. So our buoy, which we just pulled out for the end of the navigation season about a week ago, measures the vertical profile of velocity. So if you go to the Great Lakes Research Center website at Michigan Tech and scroll down till you see a picture of a boat lifting a buoy, click on the buoy and that'll take you to the buoy site. You can put in any date and take a look at the velocities of that. But we see velocities that, first of all, they're very oscillatory. They flow one day into Lake Huron, next day back into Lake Michigan, and they're driven again by all the things that Pengfei has talked about. It be happening on both of the lakes. So to get the flow right, you have to solve both lakes simultaneously. But the flows get very, very strong, 1.5 meters per second, 3 to 4 miles an hour. And then they stop and reverse. And we have a new project to put a series of high frequency radars in the Straits of Mackinac. Those are current measuring devices. So they will produce 24/7, 365 days maps of the surface currents in the Straits, and that should go operational next year. We're building those systems and getting them deployed right now. So stay tuned for that. It'll be another good Husky bike talk.
No, that's a good point. And this is a quick question from Bill. Has anyone in other countries reached out to Michigan Tech for a review of their freshwater assets? Because clearly we've got a whole bunch of expertise here. But, you know,
occasionally, we, you know, kind of a turnaround on Bill's question. We work very closely with colleagues on the Canadian side. So just because there's a border across every lake except Lake Michigan doesn't mean that we don't work together with our Canadian partners. But occasionally we do get requests for other lakes, and there's been a lot of work on other large lakes of the world, like Lake Baikal and things like that. So there is a lot of collaboration.
Well, and the $2 billion figure, that included remediating the the shoreline and restoring the habitats to the best extent possible, right?
Absolutely, absolutely. That's a sum total of everything that you can assign a value to, and it was a very difficult thing to, how do you assign a value to changes in your way of life and things like that. So, yep.
All right, Pengfei, one last question or remarks.
Yeah, I think that's this just a great opportunity, and thanks, Jen. Thanks for having me to have this opportunity to share our modeling work, and I'm glad to see there are so many questions. And please just send the question by email and contact me and Guy, and we're happy to answer. And I think this is a great experience. And thanks, Janet.
Well, it's my great honor to have you both on the show. And so Guy has posted an email. How did you do that? You did that in the message. And so good, both your emails are up there. So Pengfei's is pexue@mtu.edu and Guy's is gmeadows@mtu.edu. Thank you both. What an honor to have you both here. I'm so glad your father made math fun for you, Pengfei, because clearly it has made a difference in our lives here up in the Great Lakes area. And a pleasure to spend the evenings with you. Thank you, everyone in the audience for joining us. And please do not hesitate to send an email to either Dr. Meadows or Dr. Shea if you have any remaining questions. We'll see you next week. We're going to learn about lake effect snow, even more about this whole wind, cold, warm lake, cold air conundrum. So I think we're going to learn a lot about that next week. Thank you, everyone. Thank you, Sue, for running the show, and have a good evening, everybody.
Thank you.